مساء الخير. احنا بالدرس الماضي بالchapter 13 equilibrium of a solid or equilibrium of a body كنا خلصنا هدفين من الدرس وهن كتير مهمين. رح نرجع نعمل summing up عليهم هن اثنيناتهم. أول شي principle of interaction. If object A, as you can see here, if object A, this is object A and this is object B. If object A exerts a force on object B, if A on B, force A on B, then B exerts a force on A, if B on A. This is FB on A. This is the force exerted by B on A. This is the force exerted by A and B, such that force FA on B equal minus force FB on A. This is the principle of interaction. We have two objects. They are interacting by two forces. Each one is exerting a force on the other one. A exerting a force on B and B exerting a force on A. These two forces, as we have said, have the same line of action, the same magnitude, same line of action, which is this, the same magnitude. They are the same or equal, and they are opposite in directions. This is to this direction and this one is to this direction, such that these two forces, we say that force FA on B equal minus force FB on A. In magnitude, when we remove the vectors, we remove also the minus. We say FA on B equal FB on A. This is the principle of interaction. About the principle of equilibrium, we have one object here. In the principle of equilibrium, we have one object. Let's say the object is S. When an object is in equilibrium, forces acting on it are balanced. So here, this force S is under the action of two forces, F1 and F2. These two forces are balanced, or we can say they cancel each other, so they set the body S in equilibrium or at rest, and it doesn't move. This means that S doesn't move. We say that condition of equilibrium as a vector relation, F1, force F1 plus force F2 equals 0 vector. This is the vector relation. Or we can say also that F1, force F1 equal minus force F2. In magnitude, we say F1 equal F2. For example, these two forces have the same magnitude. F1 equal F2 equal 20 newtons. The same here as the condition of equilibrium also. We say that these two forces have the same line of action. Let me mark it with a marker. The same line of action, which is horizontal, as you can see here. The same magnitude. They are equal in magnitudes, and they are opposite in direction. This is summing up for the first two objectives explained in this chapter. Now we are going to turn to the third objective of this chapter, which is Hooke's law. It's a very important law, and it's a very important part in this chapter. Okay. First, we start with the experiment that Hooke's executed. The materials he used a spring. This is the spring. He used a support. This is the support. Okay. Masses. These are the masses. Here we see one mass, and we will connect more masses to this to do this experiment, and a ruler. As you can see, this is a ruler. Let's start with the experiment. Before starting with the experiment, let me show you something. Here we have the spring with a free end. No mass is connected to the end of it. We say that this is the initial length of the spring, L0. No mass is connected to it, or the spring is applying no force. So L0, we measure the spring, and it's the initial length. When we start connecting masses, as you can see here, this is a mass M. The spring elongates to a length L. يعني بيطول spring بس نعلق فيه mass. Okay. And here we have the length L. As you can see here, this is L0. The initial length is shorter than L, which is the uh, length when the mass M is connected to the spring. Change the mass and record the corresponding value of the length L in the table as the following. We have these masses: 50 grams, 100 grams, 150 grams, 200 grams, and 250 grams. And we will record down the lengths of the spring when we add each mass. So let's study the table and see the values. Let's go to the PowerPoint, or let's stay here. So here we have the masses and the lengths. We are going to record them here. In this experiment, we are going to study many values: the mass, the weight, and the x, which is the elongation of the spring, which is this, the distance from here to here, how much the spring is elongating. قديش طول هيدا spring, which is called delta L. This is delta, which symbolize the variation of the length, or x. You can use both delta L or x. Okay, so these are the masses, and we are going to record the lengths that we get as 0. When we have the mass 0 here, the length was 47. The length was 47 centimeters. When we load the spring with a mass M, which is 50 grams, the length became 55 centimeters. Also, adding masses 100 gives a length of 63, 150 gives a length of 71, 200 grams gives a length of 79, and 250 gives the length of 87 centimeters. What are we going to study in this experiment? As you can see, as we connect masses, as we add masses to the spring elongates more. The spring elongates more. Length when unloaded, free end of the spring, L0 was 47 centimeters. So for M equal 50 grams, let's change it to kilograms. We have mass in grams and we have mass in kilograms. This table is very important and you're going to record it as it is. So we change the mass from grams to kilograms, and we record the values here. Weight is mass times gravity. Weight is the weight of the mass added here. Each mass, we calculate its mass and we write them down here. As we said, when the mass is 0, the length of the spring was 47, which is the initial length. In this 47 is L0, so L0 is 47 centimeters. How to calculate X or delta L? Is L minus L0, L minus L0, L minus L0, L minus L0, L minus, and you can see the calculations here. For the first one, which is 55, not as you can see in the table, it's 55. Here it's a print mistake. 55 minus 47, or let's take it for 54 minus 47 equals 7 centimeters. 7 centimeters. In centimeters, here we say that delta L, or the variation of length in the stall spring, is 7 centimeters. 7 centimeters. Let me change this to 54. 54 and not 55. Okay, 54 minus 47 is 7 centimeters. We record them here in centimeter. And 63 minus 47, we write it here. 71 minus 47, we write the answer here. And then we change them to meters, we get in the table, as you can see, masses in grams and masses in kilograms. We have the weight, which is mass times gravity, and you know that the weight units, SI units of the weight, Newton is weight, mass in kilograms, and gravity in Newton per kilogram. So we get weight here 0, 0.51, 1.52, 2.5. L, the length of the spring, first when it is 0, L0 is 47. Then we, by the ruler, we record these values here. These values increases as we increase the masses. So the length, the spring will elongate, and this elongation is due to the addition of masses. Now we calculate the delta L, or variation, or x, which is also delta L, and it is the elongation. How much is the spring elongated? X equal L minus L0. At the first, when the mass is 0, the spring was 47, 0, and no elongation here. 47 minus 47 is 0. When the mass, as we said, this is 54, or here 55. 55 minus 47 is 8 centimeters. 63 minus 47 is 16. 71 minus 47 is 24. 79 minus 47 is 32. And 87 minus 47 is 40. These are the elongations of the spring in centimeter. And now we convert them to meters. As you know, from centimeter to meter, we divide by 100. 8 over 100, 0.08, 0.16, and we record the values here. These are the calculations or the data collections of the experiment. When we plot these values on a graph, as you can see here, graph showing the variation of weight as a function of elongation. Variation of weight as a function of elongation. So we take the weights. Here are the weights. We take them. We take the weights and we put them on the vertical axis, which is the y-axis here, axis of weight in the newtons. As you can see, the scale here, each one unit is 0.5 newtons. We plot them here and with their corresponding elongations. When the weight was 0.5 newtons, the elongation was 8 centimeters or 0.08 meters. Let's see on the graph. On the graph, it's in meters, so we plot them 0.08 here. Then the values, we plot the values, and we get this graph. This graph, as you can see, it is a straight line passing through the origin. What does this mean? This means that the weight in a newton is proportional to the elongation of the spring. Weight is proportional to the elongation of the spring. These are the values of the weight. These are the elongations. Now let's interpret the results more and do more further calculations, and we divide W over X, weight over elongation. We get 0.5 or 0.8, 1 over 0.16, 1.5 over 0.24, 2 over 0.32, 2.5 over 0.4, as you can see in the table, and we get what? A constant. We get a constant value, which is 6.25, and its Newton is Newton per meter. Its unit is Newton per meter. As a result, or here the conclusions. As a result, the calculation shows that the quotient W over X is constant. All the fractions gives the same value, which is 6.25 Newton per meter. On the other hand, the graph of W vs X is a straight line passing through the origin, linear function. Here is the graph. It is the linear function. It is a straight line passing through the origin. These are the conclusions. Thus, the force applied to the spring, which is the weight here, is proportional to the corresponding elongation. And you can say that this is the statement of Hooke's law, that the force applied to the spring is directly proportional to the corresponding elongation or elongation. Hooke's law statement: the elongation or compression هلا شوي بقول لكم شو يعني compression. The elongation or compression of a spring is directly proportional to the applied force. يعني هون قديش عم يطول spring هو نتيجة شو الفورس اللي عم نعمل. F equal K times X. Where do we get this this F is here. W over X, which is the force. The force is the weight. Okay. K times X. What is K? K is the stiffness, where K is called the stiffness constant of the spring in a Newton per meter. X is the elongation or compression. In units, F equal K times X. K in a Newton, K in Newton per meter, X in meter. Then we get that the force applied is in Newton. So this force may have two names. This force applied on the spring may have two names. It is the weight, as you can see here in the table. It is the weight, or as we have learned before, that when a spring, when we connect a mass or we hang a mass to a spring, after a certain time, this mass will be at equilibrium under the action of two forces, the weight of the mass and the tension of the spring. So W equal T equal mass times gravity. So this force may be W equal K times X, or maybe T equal K times X. And in general, we name it the applied force on the spring F. We name it the applied force on the spring F. Here, this خليني أحكي ببساطة. F ممكن نقول عنها الويت، كمان ممكن نقول عنها شو tension of the spring T. But in general, we say that F is the applied force. We can name it W, we can name it T. Here, these two forces, W and T, are having the same line of action, the same magnitude. Yani W equal T equal mass times gravity, but opposite directions. Okay. Remarks. The spring starts exerting a force the instant it elongates or compresses. ايمتى هيدا spring ببلش يعمل force، يعني ببلش يعمل elastic force او tension؟ لما بنعلق فيه mass. قبل ما نعلق فيه mass ما بيعمل ولا اي force. Hooke's law can be stated as the force of the spring is proportional to its elongation. يعني الفورس اللي عم يعملها spring اللي هي هاي او الويت اللي هي هاي is proportional to the elongation. قديش بيطول هيدا spring هي نتيجة شو is due to the force applied by the spring, and the force applied by the spring may be the weight or may be the tension. But these two forces, as you know, the weight and the tension, are balanced. They may cancel each other, okay? Are balanced in W equal T. A spring has elastic limit. Each spring has elastic limit. يعني أنا عندي رسور وبيطول عنده elastic limit، مثلا ممكن يطول 20 سنتيمتر زيادة elongation. إذا شديته أكثر من 20 سنتيمتر بينتزع. A spring has elastic limit beyond which، يعني أكثر منها it does not get back to its original length. يعني شديته أكثر من 20، إذا عنده limit 20 مثلا، شديته أكثر من 20 ما عادش بيرجع مثل ما كان بالسابق، خلص بينتزع. Elongation is delta L or X equal L minus L0, while compression هاي اللي قلت لكم بحكي عنها بعد شوي. Compression is delta L equal L0 minus L. لأنه spring ممكن نستعمله بحالتين، ممكن أعلق فيه أنا بكعبه ماس ويصير يطول، وممكن حط عليه من فوق مثل بهيدي الإكزامبل هون، حط عليه من فوق أنا ماس بصير شو يقصر. بالكمبريشن بهيدي حالة الكمبريشن، هيدي الكمبريشن هون، اوكي هيدي compression شو فينا نكتبها؟ compression شو بصير؟ بصير بالعكس، لانه ال L0 هي اطول فاليو للسبرينج، بتصير L0 minus L. بالعكس elongation L minus L0 لانه بصير يطول سبرينج. بالكمبريشن L0 هي اطول شيء minus L لانه بصير يقصر السبرينج. Let's do this application. The adjacent figure shows within the elastic limit of a spring the variation of the elastic force F as a function of the elongation delta L of the spring. We have here, this graph shows the variation of tension as a function of elongation. Here, this graph, or let me go back to the graph here. If you can't say graph showing the variation of weight as a function of elongation, you may say that you may write the title here as the calibration of the spring. Calibration of the spring, which is the graph showing the variation of weight as a function of elongation. Or if we have tension here, we say that graph showing the variation of tension as a function of elongation. In this application, we have the variation of tension as a function of elongation. Tension, elongation, okay, or calibration of the spring. Referring to the graph, complete the table. The quotient K represents complete the table. Let's complete the table. At 2, when tension is 2, the delta L is what? Is 1 centimeter. You take this vertical line here and then make its orthogonal projection on the horizontal axis. You get 1. Okay. When the elongation is 2, you take this vertical line here and you take then its orthogonal projection on the vertical axis, and it is 4. And when the tension is 6, also the same, 6, you get 3. Okay, T over delta L in centimeter, 2 over 2 over 1, you get 2, then 4 over 2 you get 2, then 6 over 3 you get 3. So K, the stiffness of the spring, or the spring constant, is T over delta L. 6 over 3, for example, is 2 Newton per centimeter. 2 Newton per centimeter. The application 4, this is the homework. I want you to do it. هلا ابعتلكم انا الصور على الواتساب لكم و يكون معكم اياهم. Summing up this chapter, we have 3 main objectives in this chapter. Principle of interaction. If object A exerts a force, هودي اللي لازم تحفظون بكل هيدي chapter. If object A exerts a force on object B, F A on B, then B exerts a force on A, F B on A, such that force F A on B equal minus force F B on A. As you can see here, we have 2 objects A and B and 2 forces FA on B and FB on A. These 2 forces have the same line of action, the same magnitude, but opposite directions. This is the first objective. The other objective, principle of equilibrium. When an object, here we have one object. When an object is in equilibrium, forces acting on it are balanced. We have an object S, it's under the action of 2 forces F1 and F2. These 2 forces are balanced, or we can say that the condition of equilibrium here is F1 force plus F2 force equals 0 vector, which is the vector relation, or you may be asked to write the condition of equilibrium, or this is, we can name it the condition of equilibrium. Okay, هعملكم اياها بالاحمر. هيدي condition of equilibrium. Okay, or thus من هيدي relation فينا ناخذ ال F1 equal, بس اخذ ال F2 بتصير minus F2 vector in magnitude. F1 equal F2 as I have showed you in this experiment here, in this experiment of Hooke's law, which is weight and tension, they are balanced in magnitude. W equal T equal mass times gravity. This is the principle of equilibrium. In Hooke's law, the elongation or compression of a spring is directly proportional to the applied force. قلنا الapplied force ممكن نسميها ال weight of the mass, ممكن نسميها tension of the spring، لأنه في عنا equilibrium يعني ال weight with tension are equal. Okay, and the relation we get from Hooke's law is F equal K times X, or فينا نكتب T equal K delta L. فينا نكتب T equal K X tension in T. فينا نكتب كمان weight لأنه T والويت هون are equal weight equal K X. مهم بس نشوف X أو دلتا L يعني elongation. بس نشوف tension and weight يعني في equilibrium اثنيناتهم يساوي بعضهم، أو F is the applied force in general is the applied force on this spring. هيدا كان درسنا خلص. في عنا هيدا general exercise اللي قلتلكن عنه، هيدا رح سوولكن اياه وابعتلكن اياه الابليكيشن فور، بكون معكن اياه homework. يعطيكن ألف عافية.